Hello, Mr. Simpson back here again. Still working on Chapter 1. This time we're in Section 1.5, Measurement, Uncertainty, Accuracy, and Precision. Here are our learning objectives for this section. And I'm going to emphasize this one right here because significant figures play a very important role in chemistry. So in general, quantities derived from measurements other than counting are uncertain to varying extents. Counting values are the only really exact numbers, along with known values like these conversion factors. 1 foot is exactly 12 inches. So there is no uncertainty in these relationships. Other than that, there is some level of uncertainty in all of our measurements. In general, when recording a measurement, you're allowed to estimate one uncertain digit. The first thing that we should do before ever making a measurement with an instrument in the laboratory is to take a second to evaluate the resolution of the instrument. If I take a look here at the graduated cylinder, I'm going to take a second before I get to this part of actually reading the meniscus and recording my value. I'm going to start here and take a second to try to determine what the lines on the measuring device are telling me. As I look at this, I can see that this line is 10, this line is 15, and so each of these lines in between here represent the ones place. 11, 12, 13, 14, 15. So that is what I know precisely for this instrument. I know to the ones place. The rules allow me to estimate one uncertain digit. So I need to, in my mind, think about the amount of space between the ones places, and I like to say we are allowed to read between the lines. A closer look over here, I know that this value is 20, this value is 21, this value is 22. So, of course, when I read my meniscus, I want to read the lowest part of the meniscus when making my reading. I know precisely this value to the ones place. It's above 21, but below 22. Now, the rules for significant figure and measurements allow me to estimate further. So, I should be recording this value to the tenths place. Now, here's where the estimation comes in. I'm going to look at that. I'm going to say 21.6. The units here on the graduated cylinder are milliliters, so always remember your units. This is very important because this value that I've just measured is going to be used further along in calculations. The question is, if somebody had recorded this measurement as 21.5 milliliters, would they have been correct? The answer is yes. 21.7 milliliters, also correct. We are allowed to estimate one digit further than the resolution on the device. Now, if somebody had recorded 21 milliliters, this would not be correct. They have not indicated the proper amount of significant figures based on the measuring device that they're using in this particular example. As we talk about significant figures in this video, we're going to approach them in 3 different ways. 1 sig figs in measurement, which is what I just showed you here. 2 rules for sig figs. I'll give you these rules in a minute, but basically this means when I look at a value, I need to be able to quickly identify how many significant figures are in that measurement. And finally, sig figs in calculations. Let's take a minute to do a quick practice. Here are some graduated cylinders. Record the value in each example. So as I look at this first example, I quickly determine the resolution to be the ones place. Here is 50, 51, 52, 53, 54, 55, 56, 57. You get the point. So that means I should be recording to the tens place, one additional digit. I'm going to look at this and say the meniscus here is right on the line for 56. So I'm actually going to record this value as 56.0 milliliters. Just writing 56 would not have been correct, even if I think it's directly on the line, because again, I know precisely to the ones place on this instrument that requires me to record my measurement to the tens place, one additional digit. In this example, I have 3 and 4. So now these lines in between represent the tenths place. So I should be recording my value here to the hundredths place. So this would be 4.1, 4.2, 4.3. So I know precisely 4.3. And I'm going to estimate here 4.34 milliliters. Again, the resolution of my device is to the tenths place, so I need to be recording one additional digit to the hundredths. In this example, we're back to a resolution of the ones place. So 21, 22, 23, I know precisely to the ones place, and I'm going to say that's 23.5 milliliters. Okay, next, rules for significant figures. And there are basically 5 rules. The first rule all non-zero digits, that's 1 through 9, are significant. So a value of 1.54 grams would have 3 sig figs. As I said, there are basically 5 rules. So that means the other 4 rules have to do when is a zero significant and when is it not. So first, captive zeros. Those are zeros between non-zero digits are significant. So 101 milliliters has 3 sig figs. Doesn't matter if there's a decimal point here, 1.01 milliliters, also 3. Doesn't matter how many zeros, 10.01 milliliters would have 4 sig figs. Next, zeros in front of non-zero digits are not significant. So this value here has two significant figures. These zeros in front here are not significant. I have to put them there. I can't, they're placeholders. I can't just put a decimal and leave some arbitrary amount of space. So they're going to be there, but they are not significant. Next, trailing zeros are not significant. One caveat here, unless there is a decimal. So trailing zeros are important because we're going to have to do a fair amount of rounding. So if I had a value of 36,482 and I needed to round and record this value with only two significant figures, there's one significant figure, there's two. I'm going to go one place further to determine if I should leave this value the same or round it up. So since this is less than 5, I'm going to leave this as a 6. And I'm going to record this value as 36,000. So trailing zeros are not significant for that reason, because I have to be able to round and record answers with the proper number of significant figures. Every year I've been doing this, I will come across an example where somebody will take this value and give me a final answer of 36. Hopefully we can see the problem here. I always say the same thing. If I owed you $36,482, could I give you 36 bucks and we call it even? Clearly the answer to that is no, so do not change the magnitude of your value by just dropping numbers off here. I need these trailing zeros to hold the magnitude of the value. Now, as we've seen, sometimes zeros are significant. And so if I have a value that I need to make the zero significant at the end, all I need to do is put a decimal point. So 150 has two significant figures. That trailing zero is not significant. But if I put a decimal point here, that zero is now significant, so now it has three significant figures. Our last rule zeros at the end of a number and to the right of a decimal are significant. So prior to a conversation here about significant figures, if I asked you what is the difference in magnitude or amount between these two values, you would have likely told me nothing. There is a difference between these two values, and that's the number of significant figures they have. If I were going to put a zero at the end of a number and to the right of a decimal, well, it doesn't really affect the magnitude of my value, so it must be important. It indicates a significant figure. This would have 3 sig figs. Let's take a second to look at some examples here. In the first section, I want to be able to quickly, based on the 5 rules I just gave you, look at a value and determine how many significant figures there are. In the second section, I need to be able to also round. So in this case, I want to round everything to 3 significant figures. Go ahead and pause the video, take a second to look at these and see if you can get them answered. So I'm going to quickly go through here. This first one would have 6 significant figures. All of these are non-zero digits, and that's a 0 at the end of the number and to the right of a decimal, so it's significant. B would have 4 significant figures. These two are non-zero digits, and these are captive zeros, so they are significant. So 4 significant figures. This value, 5 significant figures, non-zero, non-zero, captive zero, non-zero, and a 0 at the end of a number, n to the right of a decimal, significant. This value would have 2 significant figures, significant, significant, and these are all trailing zeros, so they're not significant. There's no decimal point there. This, 6 significant figures, non-zero, 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 captive zero, non-zero, non-zero, all significant. Letter F has 4 significant figures. These zeros are in front of a number, so they're not significant. So this non-zero digit, this non-zero digit, this non-zero digit are all significant. And again, 0 at the end of a number and to the right of a decimal is significant. Here we have 3 significant figures. Here we would have 4 significant figures. And finally, here we would have 2 significant figures. That's a trailing 0 with no decimal point. It is not significant. I'm going to skip A for a second, and we're going to do some rounding here to 3 significant figures. So 1, 2, 3, that 7 rounds it up. So this would be 5.46. Now again, these zeros here are not significant. So there's 1, there's 2, there's 3. So this would be 0.000877. 3 significant figures, there's 1, there's 2, there's 3. So 4.54. The 6 here would round that 3 up to a 4. Here I would have 43.7. And here, this is the money example I gave a moment ago. 1, 2, 3, 8, 7, 6. Now I can't just stop there and drop those other digits off, because the number then changes pretty significantly. So these become trailing zeros that are not significant. Back to this first one. That is significant. That is significant. And now I have a bunch of trailing zeros that are not significant. So one of the things that can always help me here is scientific notation. So I could record this value as 1.20 times 10 to the 5th. Now, I only need to ever look at the front part of a scientific notation to determine significant figures. I don't need to worry about moving the decimal and taking care of the magnitude of this value. 1.20 has 3 significant figures. Okay, the last part of significant figures is significant figures in calculation. So I have to first be able to make a measurement and record my measured value with the proper number of significant figures. Then when I take those values and plug them into a calculation, I need to record my final answer with the proper number of significant figures based on the measurements and the measuring devices that I was using. So there's actually 2 sets of rules here, one for addition and subtraction and one for multiplication and division. So we'll start with addition and subtraction here. If I gave you the values 12.11 plus 18.0 plus 1.013, and you plug those into your calculator and hit 0 or hit equals, your calculator would say 31.123. So the rules for significant figures in calculation state my answer cannot be more precise than the least precise measurement from which it was calculated. So what does that mean in addition and subtraction? It means the least amount of decimal places. So this first value has 2 decimal places. This one has 1 decimal place. This one has 3 decimal places. So my final answer here cannot have more decimal places than the least amount of decimal places in the calculation, which would be 1. So I would have to record this final answer as 31.1. Now, how does that work for multiplication and division? Multiplication and division aren't affected by decimal places. They are affected by significant figures. So if I was working a problem where I had to multiply 4.56 times 1.4, if If I plug those two values into my calculator, hit equals, my answer in my calculator is going to say 6.384. If you haven't figured this out by now, gone are the days of the professor telling you how to record your answers. You will be held accountable to record all your calculations throughout the year in chemistry with the proper amount of significant figures. It is very important that you learn all these rules now, or they will haunt you the entire year. Same process. My answer cannot be more precise than the least precise measurement from which it was calculated. Now, in multiplication and division, I'm not looking at decimal places, I'm looking at significant figures. So when I go back here, this is where the rules for significant figures come in. And I quickly look at these two values. This one has 3 significant figures, all non-zero digits. This value has 2 significant figures. So my answer cannot be more precise than the least precise measurement from which it was calculated, must then have only 2 significant figures. So I would record this value as 6.4 as my final answer. You can see how this would work in a simple water displacement density problem. If I take a look here, I have a volume initially of 13.5 milliliters. I put my metal, in this case rebar, in, and I get water displacement to determine the volume of the metal. So the final volume is 22.4 milliliters. So to get the volume of the metal, I would subtract those two values. Since I'm subtracting, I need the least amount of decimal places. In this case, they both have 1 decimal place. And I would get an answer for the volume of this metal as 8.9 milliliters. Well, now density equals mass divided by volume. I would plug the mass of my metal in on top. The volume of the metal that I just calculated on the bottom, and divide those two values. Now I'm using division, so it's the least amount of significant figures, which is 2. The mass has 5 sig figs, the volume only has 2, and I would get a final answer of 7.8 grams per milliliter. The last step in this section is to discuss the difference between precision and accuracy. These tend to be 2 terms in chemistry that are thrown around haphazardly, so it is important to understand the difference between these 2 terms. Precision is how close your measurements are to one another. If you do multiple trials in the same manner, you have a precise values if they're close to one another. And accuracy is how close those values are to the accepted or true value. So you may have seen this before. Pretty typical analogy here is the dartboard analogy. If in all 3 of these cases, we're going to throw 3 darts, and the goal here is to get them in the bullseye. If the first 3 darts hit here, here, and here, and in the second dartboard, the next 3 darts hit here, here, and here, and of course when I step up to throw my 3 darts, they're going to hit here, here, and here. So in terms of accuracy and precision, this first example would be precise because all 3 darts are close to one another, but not accurate because they're not near the accepted or true value or where we want them to be. In this second example, the darts are neither accurate nor precise because they're not close to one another and they're not close to the bullseye. In this final example, the darts are accurate because they're near the bullseye, and they're also precise because they are near one another. Accuracy and precision are very important when we evaluate data. If I look at 3 different data sets here, let's say the accepted value for each dispenser should have been 296 milliliters. As I take a look at this first dispenser, these values are close to one another, but they're pretty far from the accepted value. So these are precise, but not accurate. In this case, they're closer to the accepted value, and when I averaged them out, they would probably be really close to 296, but that doesn't have great precision because I go from 293 all the way up to 298. So better accuracy, but less precision in the second dispenser. And in this third dispenser, you can see I have good accuracy and precision. That's it for this section. My apologies for the length of this video, but as I mentioned during the video, significant figures are incredibly important, and if not learned at the beginning of the course here, it'll be something that will affect you all the way throughout the year, making measurements in the lab and doing calculations.